Okay, this video builds upon the ideas we have established in parts 1 and 2 of integration by partial fractions. Of course, this is part 3. In this case, we'll look at the case where the denominator factorizes into repeated linear factors. Okay, so here the rule we're going to add is that each power is going to lead into a separate partial fraction. So here you're going to have a cluster of repeated linear factors, and each power there is going to lead to a separate partial fraction. Let me demonstrate what I mean here. So for instance, if you have a factor x plus 2 to the power 3, okay, so here, since we got power 3 here, there are going to be like 3 factors that you can extract from this cluster. The first one is going to be x plus 2 to the power 1. And then the next one is going to be x plus 2 to the power 2. And then the third one is going to be x plus 2 to the power 3. So when it comes to partial fractions, then each of these is going to have a separate partial fraction. Just to sort of further explain this in terms of factors of numbers, imagine that we wanted to do the prime factorization of 24. So if we divide this by 2, then we can write this as 2 times 12. And then 12 is still divisible by 2. Going to be 2 times 6. 6 is still divisible by 2. Is going to be 2 times 3. So, and then this we can write as 2 cubed times 3. But notice that in 2 cubed, there are 3 factors of 24, namely 2 to the power 1, which was this one. Then also 2 to the power 2 is a factor of 24. And then 2 to the power 3. So 2, 4, and 8 are all factors of 24, which are like in this group or cluster of terms. So that is where this is coming from. All right, so with that, let's look at some examples of how to integrate rational functions where a repeated linear factor occurs. All right, so suppose we've got these integrals here. So we're going to start off with a. We've got 3x over x squared plus 4x plus 4. So if we factorize x squared plus 4x plus 4, this gives us x plus 2 squared. So since this has a root of multiplicity 2, it's going to give us 2 partial fractions corresponding to the powers 1 and 2. So we're going to have a over x plus 2 to the power 1. Then we're going to have b over x plus 2 to the power 2. Then again, clearing fractions is going to give us a into x plus 2 here. And then this is just going to be b. And then this time we only have one root, which is negative 2. So if we plug in negative 2 here, it will give us negative 6. This term is going to disappear. So straight away b is negative 6. Now, since we have got only one root, then for the other value, we can plug in any other value of x. Okay, it doesn't matter really. So because this equation here is true for all values of x, so it's up to us. If we plug in 0, for instance, then this side is going to be 0 and this side is going to be 2a plus b, but we already know that b is -6, so this is going to give us 2a is equal to 6, and so a is going to be equal to 3. You can check to confirm that if you try any other value of x here, you get exactly the same solution. So we're going to plug in -6 here and 3 here. So our integral is going to look as follows. So we're going to have integral of 3 over x plus 2 minus 6 over x plus 2 all squared. Okay. Then this one is just going to integrate to 3 ln of x plus 2. And this one, you must be careful with this one, is just going to integrate to 6 over x plus 2. Many students will get caught out on this one and write it as ln of x plus 2 squared. It's actually just 6 over x plus 2. You can use the method of use substitution here just to confirm. Okay, so then for example number B, we have the integral of 3x plus 5 all over x cubed minus x squared minus x plus 1 dx. The denominator here, we could factorize it using the rational root theorem. However, this is one of the examples where simple inspection shows that we can factorize this by grouping. So if we group the first and the third terms, we're going to have x cubed minus x. Then the second and the last we can write as x squared minus 1, like that. Then we're going to factor out x here. So we're going to have 3x plus 5 all over x into x squared minus 1 minus x squared minus 1. Then now we can factor out x squared minus 1, and then that's going to be into x minus 1. Then x squared minus 1 is x minus 1 times x plus 1. So it's going to be x plus 1 into x minus 1 squared. So we've got a repeated linear factor there. So that means we can write this as a over x plus 1 plus b over x minus 1 plus c over x minus 1 squared. So again, this cluster of factors gives us two partial fractions. So this time, if we clear the partial fractions, on the left hand side we're going to have 3x plus 5, which is this numerator. On the right hand side we're going to have a into it's just going to be x minus 1 squared. Then we're going to have b into x minus 1, x plus 1, and then c times x plus 1. Then if we plug in the respective roots, of plug in x is 1, the left hand side is going to be 8, the right hand side is going to be 2c, because these two are going to vanish. So that tells us that c is 4. We plug in x is negative 1, that's going to be 5 minus 3, and x is negative 1. This is going to be 4a. This is going to vanish and that's going to vanish. So that tells us that a is 1/2. Then now we've run out of roots. So as before we try any other value of x, we're going to plug in 0. Left hand side becomes 5. Right hand side is going to be a minus b plus c. However, a and c we already know. So a is equal to 1/2 and c is equal to 4. So solving this, we find that b is negative 1/2. So our integral here, we can now write as follows. So I is going to be the integral of, so a is 1/2 x plus 1, b is negative 1/2, so minus 1/2 x minus 1, c is 4 x minus 1 squared. Right, the integral of the first one is simply going to be 1/2 ln x plus 1. The second one, 1/2 ln x minus 1. And then again, this one is going to be negative 4 over x minus 1. It's not going to be a ln. These two we can combine using properties of logs. So that's simply ln of x plus 1 over x minus 1 minus 4 over x minus 1 plus c. Right, so at this point we are going to suggest that you have a go at c. You can pause the video, work through it, and then when you continue, then you're going to find our solution. All right, we're now going to scroll down to our solution of part C. Of course, if you've got any questions on any of the material we do, please do post your comments or your questions in the comment section, or indeed any other comments, or if there are particular topics that you'd be happy for us to do, just drop them in the comment section. And of course, please do not forget to subscribe and like the video and share accordingly. All right, so for part C, if we factorize the denominator, this is what we're going to get. And then in this denominator, x squared is the repeated linear factor. So this is going to give us two partial fractions. The first one power 1, second one power 2, and then of course this is the third one. By the way, as a general rule of thumb, if this is a cubic, when you resolve this into partial fraction, there must be 3 unknowns. If this is a quadratic, there must be 2 unknowns. So the number of unknowns should always correspond to your degree of the denominator. This is a polynomial of degree 4, then there must be 4 here. Okay, then if we clear the fractions, on the left hand side we're going to be left with the numerator. This is what the right hand side is going to be. Then there are two roots. First one gives us b is 1/2, the second one gives us c is -4. Then to find the third unknown, we just choose another value of x. We use 1 here. We find that a is 1. So we're going to plug in 1 here, 1 here, and 4 there. So our integral is going to look like this. Integral of 1/x is ln x. Integral of 1/x squared. Again, just be careful not to get caught out. It is not ln x squared. It's -1/x, because this is the same as x to the power -2. So you simply add 1 and divide. And then this one, since the coefficient of x here is 4, we're going to have to divide by 4. And then that means these two we can group together. They look like that. And that is the final expression. That is the final integral. Thank you.